Okay, today we're going to talk about momentum. So again, in physics, we have terms that we use in everyday life, and sometimes the terms in physics are the same, and sometimes they're a little bit different. Momentum is one of the ones where, when we use it in everyday language, it's very similar to what actually momentum is. So in everyday language, if you're kind of moving along and you say, I have a lot of momentum, and momentum in physics means the same thing conceptually, but we, of course, are going to look at it mathematically. So momentum, it says the product means multiplication, of the mass and the velocity of a body. This is a vector quantity. Remember, whenever we learn about something new in physics, we always want to say to ourselves, is it scalar or is it vector? Why is that important? Because vector quantities have both magnitude and direction. So the direction is important. Remember, scalar quantities we can add algebraically, but vector quantities we have to add vectorially, so that means that we have to add them head to tail. Okay? The unit is a kilogram meter per second, and the symbol for momentum is lowercase p, so little p. So p is equal to mv. So mass is in kilograms, velocity is in meters per second, so if we put it all together, it's a kilogram meter per second, so that's the unit. Now, if you look at this equation, you see that the momentum here is just mass times velocity. So it says the greater the mass and the velocity, the more momentum it has. So if I increase the mass, I'm going to increase the momentum. If I increase the velocity, I'm going to increase the momentum because these are directly proportional. Now, the more momentum an object has, the more momentum it can give to another object. So later on in the week, we're going to learn about when we have more than one object and we have collisions and how momentum can be transferred from one object to another. Okay? The more momentum an object has, the greater force you need to stop it. Okay? Now we're going to talk about something called impulse. So impulse is the change in momentum. So you know how momentum is p? This is delta p. Now in some books, your book doesn't have a unit for impulse, but in all the college books, they use capital J for impulse. So impulse, a product of a force in the interval. So again, this is delta p. So now when we look at it, impulse is delta p, which is equal to F delta t. But since the impulse is the change in momentum, and we know momentum is mv, so then it's going to be m delta v. Now when you have this is called the impulse momentum theorem. Am I always using it like this? No, I could just be using part of it that says delta p is equal to m delta v. Or they could say, what's the impulse? And you're given the force and the time, so then I would say the impulse is equal to force times time. Or I could do it like this, while saying this is equal to that. The best way to probably remember this is to put it all together and just say delta p is equal to m delta v, which is equal to F delta t. And if you remember it like this, you're not using all three parts. You can just use the first part. Delta p is m delta v. You could say delta p is F delta t, or m delta v is equal to F delta t. And remember, delta means a change in. So the change in would be the final minus the initial. So the change in momentum for a body is equal to the impulse, and the direction of the impulse will be the direction of the force. Because remember, it's force times time. Time is scalar, so time doesn't have a direction. So when you want to know the direction, it's going to be the direction of the force. So here's some quick little examples. A moving truck has more momentum than a car moving at the same speed, and the reason for that is the truck's going to have a greater mass, right? A fast car can give more momentum than a slow truck. And then a truck at rest has no momentum at all. So we can see this when we look at collisions involving automobiles, that if there's an accident between a truck having a large mass, like a semi, and it hits a small car, obviously the semi has more momentum because of the mass. But then there can be times when there can be a car that's moving really, really fast, and because of the speed, even though it's a car, it can also cause a lot of damage because it has that much momentum. So we're going to see how this applies to everyday life later on in the chapter. Okay, so let's look at an example. It says a 20 Newton force acts on a 2 kilogram mass. So as you're going along, you want to chunk it. So what that means is as you read it, when you write down your given, so it says a force of 20 newtons. So right away in my given, I'm going to write F as 20 newtons. Acts on a 2 kilogram mass, so that's my mass, for 10 seconds, so that's my time. Compute A, the impulse, and B, the change in velocity. So I know that impulse delta P is equal to F delta T. Now they don't give me the change in time, they give me, this is the elapsed time. So delta P is equal to Ft, so it's equal to 20 newtons times 10 seconds, so 20 times 10 is 200, and a newton times a second is a newton times a second. So some of you are probably saying, wait a second, isn't the unit for impulse a kilogram meter per second? Well, let's look at that for a second. So if we look at our units, we know that momentum is going to be mass times velocity, so it's a kilogram times a meter per second, which is a kilogram meter per second. Now, impulse is the change in momentum, which is m delta v, which is m vf minus vi, but the unit is kilogram times meter per second, so the unit should be the same. But I just did this problem, and it has a newton times a second. Well, let's look at it again. We know delta P is m delta v, which is also equal to Ft. So force is measured in newtons, and time is measured in seconds. So how can I have two different things? So let's look at this. I have a kilogram meter per second, and this is supposed to be equal to a newton times a second. Well, I know that a newton is a kilogram meter per second squared, and then times this second. So this second cancels with that, and I end up with kilogram meter per second. Are they the same thing? Yes. So we see that the unit can either be a newton per second or a kilogram meter per second, and we see that they're the same thing. Okay? All right, let's get back to the problem. So then it says the change in velocity. So here I know that Ft is equal to delta P, which is m delta v. So delta v is, remember, this is the change in velocity. Okay? So the change is delta v. So now I'm going to take this equation, Ft is m delta v. I'm going to rearrange the equation to solve for the unknown in terms of the known. Yes?
If we were to use the m delta v part of the equation instead, would you mark us wrong for putting newton per second as a kilogram?
It doesn't. You can write whatever unit you want, but you want to cancel your units to check it at the end. Okay? And again, the more you write down, the less likely you are to make a mistake. So when you write it all like this, if you can, the question was, can my final answer be a newton per second or a kilogram meter per second? In this class, you're never going to work something out and just throw the unit in at the end and say, oh, I know this is my final unit. It's going to vary depending upon what you're given. In this case, you have a newton times a second, which is a newton per second. If I was using the other equation, m delta v, and it comes out to be kilogram meter per second, I would write that as my final unit because I'm going to carry my units through and cancel them in order to check my work. But as we just saw a minute ago, we see that a newton times a second is the same as a kilogram meter per second. You're not going to be marked wrong if you wrote a newton per second or a kilogram meter per second. All right, so then I'm going to rearrange the equation and substitute in my values. Now here I have a newton per second divided by a kilogram. So what I can do is I can expand that, instead of writing Newton per second, I'll write a kilogram meter per second times a second divided by a kilogram. So again, this cancels with that. This, kilogram meter per second squared. So I end up with a meter per second, which is the correct unit for velocity. Okay? And that's why we like to carry our units through, because it's a foolproof way to check our work, check our algebra and stuff like that. All right, the second example says a car that weighs 7,840 newtons. So that's the weight. Is accelerated from rest, so that means the initial velocity is 0. Just write down your given. So VI is 0. To a velocity of 25, so that's VF, eastward by a force of 1,000 newtons. Okay? What is the car's change in momentum? Now, before you start giving up on this problem, remember that we said that the change in momentum, delta P, is all equal to m delta V. So that's going to be m, and delta is changing, so it's always going to be VF minus VI. So this is where that final and initial velocity comes into play. Okay? So where do we start? Well, if you've noticed that the equations we used all had what in it? Mass. So either you can do a conversion right away so you don't make a mistake instead of doing it. I know that weight is mass times gravity. So if I want to find the mass is going to be the weight divided by gravity, and then I could find the weight. Or, instead of actually finding the number, what I did was I substituted this in my equation. I knew that delta P is m delta V. So for the mass, I just put F of G over G, which is this, or I could just calculate it. And then delta V is the final minus the initial. I just did it because I just want to save a step. I don't necessarily recommend doing that, okay? Because when you try to substitute one equation in the other, you're more likely to make a mistake. So then I find it. And now the direction east, remember the direction is in the same direction as the force. Part B says, how long did it take the force to act to change the car's momentum? So now, how long? How long? That means the time, okay? So I know that Ft is equal to delta P. So now I just calculated this, Ft. I calculated the delta P part of it, because remember, the whole thing says delta P is Ft is equal to m delta V. So remember, this is the change in momentum, which is the impulse, which is this, which is equal to this. So I just found what this is, and now I can find the time. So Ft is equal to delta P. So this I know. This I know. And now I want to find the time. So I rearrange the equation to solve for the unknown in terms of the known. Time is equal to delta P over F. I use the answer for part A and part B, and then the force is 1,000, and then I find the time. Now again, if we want to check our answer, I carry our units through to check them. So let's look at it. So that's what I did down here. So in the numerator, you have a kilogram meter per second. In the denominator, you have a newton. So now you're going to expand that out, because a newton is a kilogram meter per second squared. And then you start canceling things. Okay? So a kilogram, and if you're not sure how to cancel it in this form, when we learned about fractions in 5th grade, we say that when you divide, it's like multiplying times the reciprocal. Okay, so go ahead and do that. You know, it takes an extra, couple of seconds, but when you do it like that, you don't make a mistake. The more you write down on paper, the less likely you are to make a mistake. So then I can easily see this kilogram cancels with that. I see that this cancels with that, this cancels with that, and the only thing I have left with is a second, which is the correct unit of time. And that's it. So that is momentum and impulse.